player's tenure in the NBA, or how long they have been playing for, is one of the best indicators on whether that player has contributed positively to the teams that have hired him. This metric can be induced and shifted based on many varying factors such as injury risk, statistical contribution, or even fit in the league. The ability to predict the length of these players' careers is therefore very valuable for teams that might think of taking up these $1 million plus contracts. Knowing how long a player might be able to play for provides them value both in the short term in terms of security and in the long term in terms of versatility. The ability to predict such a thing from a player's first season in the league would be highly beneficial. So we will aim to do just that. The plan is to try and predict the career length of a professional NBA player using statistics available only after their rookie season. This includes categorical features such as the team and the draft pick they were drafted at, along with statistics both from the box score, such as points and rebounds, and not from the box score, the advanced statistics, such as win shares and box plus minuses. The dataset that forms the backbone of this project was compiled and published by Sumitro Dana on Kaggle under the title of NBA Stats. The dataset itself was in turn sourced from Basketball Reference, perhaps the most reputable and respected database when it comes to NBA statistics. This dataset covers 78 years of NBA history, starting from its formative leagues and offshoots and rebrands, including the Basketball Association of America and the APA. Before utilizing this dataset, however, several pre-processing steps were required to clean and prepare the data. Most fixes were due to inconsistent or non-existent tracking in older eras of the NBA, such as simplifying player positions. Active players, i.e. they just played in the 2025 season, were not included in order to avoid rat censoring and ensure accurate modeling, meaning current long-serving players like LeBron James and Steph Curry will not be included. This processed final dataset was then split into training, validation, and test sets for model training and subsequent evaluation. This resulted in a training dataset which contained 3,290 rows and validation and test datasets with 1,098 rows each, including headers. These sets also comprise of 33 input features to help us predict career length. Our target variable, the number of seasons a player is in the league for, was processed to be in log form. By graphing the distribution of career length in our dataset, we can see that there is a clear noticeable skew in our dataset, peaking at one season in the league before a steep drop-off. We have a maximum of 22 seasons after a bit of a tail out on the drop, courtesy of Vince Carter, the only player who has retired after playing for such a length of time. So, how will we predict career length? First up, the shallow MLP. This is a simpler network with just two hidden layers: early activation, some dropout to prevent overfitting, and train for 20 epochs with early stopping. Basically, a lightweight network that will pick up some linear relationships in rookie stats that's fast to train without a high risk of overfitting. Then we had the wide and deep model, which combines a linear wide component to memorize straightforward correlations, plus a deeper stack of hidden layers to generalize the more complex ones. We will also use dropout, atom optimizer, and early stopping to keep it stable. This will be able to capture more complex patterns and handle both categorical and numerical values better. To measure success, we'll use four main metrics: MAE, which is the average error in seasons; RMSE, which will highlight larger misses; R-squared, which will give us an explanation of the variance; and RMSLE, which will help penalize underestimates to handle the skewed data. So, how did our models do? Well, compared to a baseline regression model that we fitted, we can see that our models have a modest improvement when it comes to both MAE and RMSE, around 5 to 7%. A drop in the R-squared and RMSLE values can be attributed to a lack of variation explanation, especially due to underfitting, as our log transformation benefits linear regression much more than it does our deep models. To improve, we will conduct some hyperparameter tuning when it comes to depth, dropout, and learning rate, among others, in order to improve our deep learning models before evaluating on a final test set and coming to a conclusion to answer our original question on whether we can predict an NBA player's career based on their rookie season stats. Thank you.